Tonight we are going to do something that no human being has ever done and will ever do. We are going to watch the universe die. Not quickly, not dramatically, at least not at first. The death of the universe is the slowest thing imaginable, a process so gradual that the entire history of civilization, the entire history of Earth, the entire history of complex life would be an imperceptibly brief flash at the very beginning of the story. We are going to travel through time, far further than any telescope can see, and we are going to watch, stage by stage, as everything that exists today fades, cools, decays, and eventually approaches something close to nothing. This is not speculation dressed up as science. Every stage we will visit tonight follows from physics we have tested, from laws we have confirmed, from observations we have made with the best instruments ever built. The timescales are almost incomprehensible. The endpoints are almost unimaginable. But the physics is real and the journey is worth taking. There are things you will learn tonight that will change how you look at the night sky. Not because the sky looks different after you know this. It does not. The stars are still there. The galaxies are still visible. The universe still looks vast and bright and ancient. But knowing what is coming, knowing the arc of the whole story, makes what we see right now feel different. More precious, perhaps, more remarkable. Because what we are looking at tonight is not the universe in its natural state. It is the universe at its peak. It is the universe at its most interesting, most complex, most luminous moment. And that moment, cosmically speaking, will not last. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now make yourself comfortable. Let us begin. We are going to structure tonight's journey as a series of eras. Each era is defined not by a specific event, but by the dominant process happening in the universe during that time. The era we currently live in. The era after the last stars die. The era of degenerate remnants. The era of black holes. And finally, the Dark Era. Each one is longer than all the previous ones combined, by factors so large that the concept of time itself starts to lose its ordinary meaning. To navigate these eras, we need a timescale. The universe is currently 8 billion years old. On a logarithmic scale, where we measure time by the number of zeros in the number of years, the current age of the universe is about 10 to the power of 10 years. I am going to use this notation throughout tonight. When I say the universe is at 10 to the power of 14 years, I mean 100 trillion years from now. When I say 10 to the power of 40 years, I mean a 1 followed by 40 zeros years. These numbers are so large that giving them ordinary names becomes meaningless. I will try to give you analogies where I can, but at some point the analogies fail and the numbers have to speak for themselves. Let us start where we are. The Stelliferous Era, the age of stars. Right now, the universe is in the middle of what cosmologists call the Stelliferous Era, from the Latin for star-bearing. Stars are forming, burning, and dying all across the observable universe. The night sky as you know it, the scattered points of light, the familiar constellations, the band of the Milky Way, all of this is the universe in its stelliferous phase. Galaxies containing hundreds of billions of stars, each star a nuclear furnace converting hydrogen into helium and heavier elements, pouring light and heat into the surrounding space for millions or billions of years. We are living in the middle of this era, not at the beginning and not near the end. Star formation has been ongoing for about 4 billion years since the first stars formed a few hundred million years after the Big Bang. but the rate of star formation peaked about 10 billion years ago, when the universe was about 4 billion years old. Since that peak, the rate has been declining. There is less free gas available to collapse into new stars. The existing gas has been incorporated into stars that have lived and died and returned enriched material to the interstellar medium. But the overall reservoir of star-forming material is slowly being depleted. The Stelliferous Era will continue for a very long time by human standards, but it is not eternal. The last stars will eventually die, and when they do, the universe will enter a phase fundamentally different from anything we have ever seen. The question is when. The answer depends on what kind of stars you are counting. The most massive stars, the ones that burn tens or hundreds of times more luminously than the sun, burn through their fuel in millions of years. They have already been gone for most of the universe's history. The stars we see today in the Milky Way are predominantly medium-mass stars like the Sun and lower-mass red dwarf stars. The Sun will continue burning for another 5 billion years before it expands into a red giant and eventually settles into a cold white dwarf. But the last stars to die will not be sun-like stars. They will be the smallest, dimmest, most miserly consumers of nuclear fuel in the galaxy. Red dwarfs, stars with masses of perhaps 10 or 20% of the sun's mass, burning so slowly and so efficiently that they can sustain nuclear fusion for periods that dwarf the current age of the universe. The least massive red dwarfs, those hovering just above the minimum mass required to sustain hydrogen fusion, can burn for up to 10 trillion years. That is 10 to the power of 13 years. Roughly 1,000 times the current age of the universe. These stars will still be burning long after the sun has gone cold, long after every sun-like star in the Milky Way has ended its life, long after the night sky, as we know it, has changed beyond recognition. The Stelliferous Era, defined as the period when stars are still actively fusing hydrogen, ends somewhere around 10 to the power of 14 years from now. 100 trillion years from now. At that point, the last red dwarf will have exhausted its hydrogen fuel and contracted into a cold, dark object. The age of stars, which has lasted for what we experience as the totality of cosmic time, will be over. The sky at that moment will be almost entirely dark. The galaxies will have lost their blue and white-hot massive stars first, then their yellow and orange medium stars, and finally their dim red stars. What will remain in each galaxy is a collection of stellar corpses, white dwarfs, the cooling remnants of sun-like and smaller stars. Neutron stars, the incredibly dense remnants of more massive stars that ended their lives in supernovae. Black holes, the remnants of the most massive stars. And wandering among these corpses, the planets. Billions of cold, dark, frozen worlds that once orbited living stars, now drifting in darkness around objects that no longer shine. The solar system of the distant future will look like this. The sun will have long since become a white dwarf, cooling slowly, its surface temperature dropping over trillions of years from tens of thousands of degrees to increasingly cold temperatures. The planets will be frozen, dark, and utterly dead. The Milky Way galaxy will still exist as a gravitational structure. Its stars, or rather its stellar remnants, will still be orbiting the galactic center. But the spiral arms, defined by regions of active star formation and lit by young hot stars, will have dissolved. There will be no active star formation, no nebulae, no supernova explosions, no new worlds being born, just the slow, cold orbital dance of remnants in the dark. Now let us advance the clock into the Degenerate Era. The Degenerate Era runs roughly from 10 to the power of 15 years to 10 to the power of 40 years from now. These timescales are so immense that even the word trillion feels quaint. 1 quadrillion years, 1 quintillion years, numbers that have no referent in human experience. What defines the Degenerate Era is the dominance of degenerate matter objects, white dwarfs and neutron stars. These are objects held up not by heat or by nuclear burning, but by quantum mechanical effects, by the refusal of electrons or neutrons to be compressed into the same quantum state. They do not burn, they do not radiate significantly. They simply cool slowly over immense timescales. White dwarfs cool remarkably slowly. The most recently formed white dwarfs are still hot, glowing blue or white. Older ones are yellow, then orange, then red. Eventually, if given enough time, a white dwarf will cool to the point where it no longer emits visible light, becoming what is sometimes called a black dwarf. A cold, dense, dark crystal of carbon and oxygen, roughly the size of Earth but with a mass comparable to the Sun. But here is an interesting fact. The universe is not yet old enough for even the oldest white dwarfs to have cooled to the point of being truly dark. The oldest white dwarfs in the Milky Way, those that formed from the first generation of stars, are still cooling. They are still warm enough to emit faint light. In the far future, all white dwarfs will eventually become black dwarfs, cold and dark remnants of once burning stars. But the timescale for this cooling is so long that black dwarfs are only a theoretical prediction at this point. None yet exist in the universe. During the Degenerate Era, another process becomes important. Gravitational interactions within galaxies, the slow gravitational scattering of stars past each other over billions of years, gradually eject some stars from galaxies and cause others to fall inward toward the central black hole. This is an incredibly slow process. Individual gravitational encounters between stars are rare, and each encounter only slightly changes the trajectories involved. But over timescales of 10 to the power of 19 years, this process acts like a gradual evaporation of the galaxy. Stars drift outward and eventually escape the gravitational pull of the galaxy. The galaxy slowly dissolves. By about 10 to the power of 20 years, most of the stars, or rather stellar remnants, in a typical galaxy will have been ejected into intergalactic space. The galaxy itself will have dissolved. What remains at the center is the supermassive black hole, orbited by a small fraction of remnants that have spiraled inward rather than outward. The rich, complex gravitational structure of the galaxy, which has persisted for billions of years, is gone. Now let us talk about something that occurs during the Degenerate Era that most people have never heard of: proton decay. In the standard model of particle physics, protons are stable. They do not decay. The proton is the lightest baryon, the lightest particle made of 3 quarks, and there is no lighter baryon for it to decay into. Conservation of baryon number keeps the proton stable. But many extensions of the standard model, many theories that attempt to unify the forces of nature at high energies, predict that protons are not perfectly stable. They predict that protons can decay very slowly into lighter particles. The lifetime of a proton in these theories is predicted to be around 10 to the power of 33 to 10 to the power of 40 years, depending on the specific theory. No proton decay has ever been observed. Experiments like the Super Kamiokande detector in Japan have been watching enormous tanks of water for decades. looking for the telltale flash of energy from a decaying proton. They have found nothing, which means the proton lifetime is at least 10 to the power of 34 years. This rules out the simplest versions of grand unified theories, but many more complex versions remain viable. If protons do decay, as most physicists suspect they do on some timescale, then the Degenerate Era comes to an end in a particular way. Every white dwarf, every neutron star, every cold dead rock, every frozen planet will slowly dissolve. The protons in all of this matter will eventually decay, releasing energy and leaving behind lighter particles. By 10 to the power of 40 years, assuming proton decay occurs at the expected rates, all the ordinary matter in the universe will have decayed. The white dwarfs and neutron stars will have dissolved, replaced by diffuse clouds of electrons, positrons, and photons. The planets will have dissolved. Every rocky body in the universe will have vanished. Even if protons do not decay through grand unified theory processes, there is another mechanism that will eventually destroy all matter on a much longer timescale: quantum tunneling. In principle, any object can quantum mechanically tunnel into a lower energy state. A white dwarf can tunnel into a black hole, an iron star, a neutron star, or any other configuration. These processes are extraordinarily improbable, so improbable that they would only occur on timescales of 10 to the power of 10 to the power of 76 years or longer. But if the universe persists long enough, even quantum tunneling will eventually transform all remaining objects. Let us continue. By around 10 to the power of 40 years, the Stelliferous Era is long over. Galaxies have dissolved, ordinary matter may be decaying, and we enter the era of the universe that is truly alien to anything we have ever experienced: the Black Hole Era. The Black Hole Era is dominated by black holes. Everything else is gone or fading. The black holes remain. Why do black holes outlast everything else? Because they are not made of ordinary matter that can decay. They are not held up by quantum mechanical degeneracy pressure that can eventually be overcome. They are regions of spacetime geometry, places where the curvature of space and time is so extreme that nothing can escape. There is no decay mechanism that applies to a sufficiently isolated black hole. They persist. But they are not completely eternal. Stephen Hawking showed in 1974 that black holes are not perfectly black. Through a quantum mechanical process at the event horizon, black holes slowly emit radiation, losing mass in the process. This Hawking radiation is extraordinarily faint for large black holes. The temperature of Hawking radiation from a stellar mass black hole is about 100 nanokelvins, far colder than the cosmic microwave background radiation that currently fills the universe. So right now, black holes are absorbing more energy from the cosmic microwave background than they are emitting in Hawking radiation. They are growing, not shrinking. But as the universe expands and cools, the cosmic microwave background temperature drops. Eventually, it will drop below even the minuscule Hawking temperature of large black holes. At that point, the black holes will begin to slowly lose mass, evaporating over immense timescales. The evaporation time of a black hole scales with the cube of its mass. A stellar mass black hole of 10 solar masses will take roughly 10 to the power of 77 years to evaporate. The black hole at the center of the Milky Way, with a mass of 4 million solar masses, will take about 10 to the power of 93 years. And the supermassive black holes at the centers of the largest galaxies, with masses of billions or tens of billions of solar masses, will take up to 10 to the power of 100 years or more. These timescales are so extreme that they make all previous timescales in this journey look like eye blinks. The entire Stelliferous Era, from the first stars to the last, spans about 10 to the power of 14 years. The time for a stellar mass black hole to evaporate is 10 to the power of 77 years. The ratio between those two numbers is larger than the number of atoms in the observable universe. And yet, given enough time, even the most massive black holes will evaporate. Hawking radiation will slowly drain their mass. As they get smaller, they get hotter, and their evaporation accelerates. The final moments of a black hole's evaporation are explosive. The last fraction of the black hole's mass is radiated away in a burst of high-energy photons and particles. And then it is gone. The spacetime geometry heals. The region that was once a black hole is now just empty space. The final supermassive black holes will evaporate somewhere around 10 to the power of 100 years from now. After that, the black hole era is over, and we enter the last and longest era of the universe's existence, the dark era. The dark era. After the last black hole evaporates, the universe enters a state that is profoundly and permanently dark. There are no more stars, there are no more galaxies, there are no more black holes, there is no more ordinary matter in any recognizable form. What remains? Radiation. The photons emitted by all the processes that came before, the Hawking radiation from evaporating black holes, the light from stellar processes in the far past, diluted and redshifted by the continued expansion of the universe to wavelengths far longer than any we can currently detect. Electrons and positrons drifting in an almost perfectly empty expanding space. Neutrinos moving at essentially the speed of light, filling the universe with a faint background of matter that barely interacts with anything. And the dark energy, the energy of empty space itself, continuing to drive the accelerating expansion of the universe. The universe in the dark era is unimaginably empty. The density of matter is so low that the average separation between particles is incomprehensibly vast. The universe is expanding, and the matter within it, such as it is being carried further and further apart. Any two electrons in the dark era universe are receding from each other at ever-increasing speed, their separation growing with the expansion of space. There will almost certainly never be another star, never another planet, never another atom in the ordinary sense. The chemistry of life, the complexity that allowed thinking beings to arise and ask these questions, is gone. The universe has used up all of that potential and will never replenish it. The dark era is not eternal, though it is so long that the concept of an ending becomes almost meaningless. Various physical processes will continue to operate on the particles that remain. Electrons and positrons, if they ever come close enough, will annihilate each other, producing photons. But in the dark era, the universe is so vast and the density of particles so low that even this process occurs with agonizing slowness. There are conjectured processes that might affect the dark era universe on even longer timescales. If quantum gravity effects allow for the nucleation of new Big Bangs, for the spontaneous creation of new universes from quantum fluctuations in the vacuum, then the dark era might eventually seed new universes. But whether this can occur, and what it would mean if it did, is entirely speculative and lies far beyond anything we can currently calculate with confidence. What we can say is that the dark era universe, dominated by radiation and a handful of lonely particles in an ocean of expanding space, will persist for timescales that make even the black hole era seem brief. The expansion of the universe will continue indefinitely, driven by dark energy. Space will grow larger and larger and larger, with no upper bound as far as we know. The few particles that remain will drift further and further apart until the average distance between them is so vast that even light, traveling since the beginning, could not have crossed it. And in that vast darkness, the temperature of the universe approaches absolute zero, but never quite reaches it. The quantum fluctuations of the vacuum, the same fluctuations that powered inflation at the beginning and that drive Hawking radiation from black holes, persist even in the ultimate cold. Space is never quite empty, never quite still, because quantum mechanics forbids perfect stillness. But the fluctuations are so faint and so sparse that the universe is as close to nothing as physics allows without actually being nothing. This is how it ends, not with a bang. Not even with a whimper in Eliot's sense, with a long, slow, unimaginably quiet cooling. The last photons losing energy to the expansion of space, their wavelength stretching to scales that have no analogy in physical reality as we know it. The last electrons drifting apart, separated by distances larger than the observable universe is today. The dark energy continuing its work, expanding space silently and inexorably, driving the remaining particles toward an isolation so complete that the universe is, for all practical purposes, a collection of separate, causally disconnected, utterly lonely particles, each in its own private horizon, each separated from every other by a universe of expanding empty space. That is the fate of the universe. That is where all of this is going. Now I want to step back from the timeline and say something about what it means to know this. Because knowing the fate of the universe is not a neutral piece of information. It changes something about how you see the present moment. We are here right now in the brief, brilliant, improbable middle of the Stelliferous Era. The era when stars are still burning, when galaxies are still forming, when there is still free hydrogen, still supernova explosions creating heavy elements, still young planets cooling from molten rock to potential havens for chemistry. When the universe is, by any measure, at its most complex, most energetic, most interesting. The era we live in is a cosmological eye blink. The entire Stelliferous Era, from first star to last, is 10 to the power of 14 years. The black hole era alone is vastly longer. The dark era is longer still by incomprehensible factors. In the context of the full history of the universe, from Big Bang to heat death, the period when stars shine and galaxies exist and complex chemistry is possible is a thin sliver at the very beginning. We are in that sliver, right now. This is the moment when the universe is alive, in the sense of being energetically active, chemically complex, physically rich. This moment will not last. It is not lasting. Every second that passes is a second deeper into the Stelliferous Era, a second closer to the extinguishing of the last red dwarf. I do not think this should make you sad. Or rather, I think the sadness is appropriate, but not the only response. Because what the fate of the universe reveals is not that everything is ultimately meaningless. It reveals that everything happening right now is happening in the rarest, most extraordinary window of cosmic time. The window when stars shine and planets form and chemistry works and complexity emerges, and apparently minds arise and look up at the sky and ask where all of this is going. We are those minds. We are here in the brief burning moment. and we are asking the question, that is not nothing. That is, in fact, everything. Everything that physics can possibly tell us about what is valuable and what is rare and what is worth paying attention to points at this. The moment when the universe is alive is the moment we are in. And the minds that arose in that moment and understood it, the minds that could trace the full arc from Big Bang to heat death and find themselves, unexpectedly, in the middle of it, those minds are perhaps the rarest thing the universe has ever produced. Let me go back through the timeline one more time and fill in some details I passed over, because each era has remarkable things happening in it that deserve more attention. The transition from the Stelliferous Era to the Degenerate Era is not a sharp boundary. It is a gradual dying of the fires. The most massive stars die first, in spectacular supernovae that briefly outshine entire galaxies. Then the intermediate stars, like our Sun, swell into red giants, swallowing their inner planets, shedding their outer layers in beautiful planetary nebulae, and leaving behind white dwarfs. Then the lower mass stars, burning longer and cooler. And finally the red dwarfs, the most numerous stars in the galaxy, burning for tens of trillions of years before finally cooling to darkness. During this long decline of star formation, the universe gradually changes color. Young galaxies are blue, lit by hot massive stars that burn briefly and brilliantly. As those stars die, the galaxy shifts to white, then yellow, then orange, then red. The universe itself, once full of blue-white hot stars, gradually reddens as only the coolest and dimmest stars remain. And then finally, even those cool red points of light fade, and the galaxy goes dark. This color evolution of the universe is something we can actually observe, at least in principle. By looking at galaxies at different distances, we are looking at them at different times. The most distant galaxies, whose light has taken billions of years to reach us, show the universe as it was in the past, when star formation was more active and galaxies were bluer. Nearby galaxies show the universe as it is now. By comparing galaxies at different distances, we can trace the history of star formation across cosmic time, and what we see is exactly this gradual reddening. The universe was bluer and more active in the past. It is getting redder and quieter now, and in the far future it will go dark. During the Degenerate Era, there are things happening that are subtle but physically important. One of them is the slow cooling of white dwarfs. As I mentioned, the oldest white dwarfs in the galaxy are still cooling. In the Degenerate Era, this cooling continues for timescales measured in quadrillions of years. A white dwarf cools by radiating energy from its surface. Its interior is a crystalline lattice of carbon and oxygen ions, supported by the pressure of degenerate electrons. It has no nuclear energy source. It is simply a crystal slowly losing heat to the surrounding darkness. The cooling process is remarkably slow because the heat capacity of a degenerate object is low and the surface area is small, being roughly the size of Earth. A typical white dwarf takes about 10 to the power of 15 years to cool from thousands of degrees to close to absolute zero. In the far future, the universe will be full of these cold, dark crystals, orbiting nothing in the dark, each one a memorial to the star that burned for billions of years before leaving it behind. Neutron stars cool even more slowly, in some respects, because their internal physics is different. Their core temperatures decline over billions of years, and their surfaces eventually cool to the point where they emit almost no radiation. They will persist through the Degenerate Era and into the black hole era, slowly cooling in the dark, until proton decay or quantum tunneling eventually disrupts their structure. Let me talk about something else that happens during the Degenerate Era: the slow, quiet death of the solar system. After the sun becomes a white dwarf, the planets that survive the red giant phase, those that were not swallowed, will continue to orbit the cooling remnant. Mars, Jupiter, Saturn, Uranus, Neptune, and the Kuiper Belt objects will remain in orbit, frozen and dark, around a fading ember. Over billions of years, tidal interactions and gravitational perturbations will slowly alter the orbits. Eventually, some planets will be ejected from the system by gravitational encounters with passing stars or stellar remnants. Others will spiral inward and be absorbed by the white dwarf through tidal interactions. But some planets may remain in stable orbits around white dwarfs for extraordinarily long times. A Jupiter-sized planet in a wide orbit might persist for 10 to the power of 20 years or more, frozen and dark, a silent companion to the cold remnant of the star it once orbited. These orphan planets, circling cold stellar corpses in the dark, are the distant descendants of the solar system we know. The fate of Earth itself is more certain and more dramatic. As the sun expands into a red giant in about 5 billion years, the inner solar system will be swallowed or dramatically altered. Models suggest Earth will either be engulfed by the expanding sun or will spiral outward slightly as the sun loses mass, remaining just outside the red giant's outer atmosphere. Either way, the surface will be sterilized long before the sun reaches its maximum extent. The oceans will boil. The atmosphere will be stripped away. The surface will melt and then solidify and then melt again as the solar luminosity changes. By the time the sun settles into its white dwarf phase, Earth will be a sterile rock, its oceans gone, its atmosphere gone, its surface transformed by heat and radiation into something barely recognizable. This is not a tragedy for the universe. It is simply the natural consequence of stellar evolution. The Earth has had billions of years of habitability. Whatever life and intelligence arises in those billions of years, including us, is a remarkable and temporary flowering. The planet will continue to exist in some form for much longer, orbiting a cooling white dwarf in the dark. But the window for complex life on Earth is finite, and we are somewhere in the middle of it. Now let me spend more time on the Hawking evaporation of black holes, because it is one of the most remarkable predictions in all of physics, and it deserves to be understood more deeply. Hawking radiation arises from a quantum mechanical effect near the event horizon of a black hole. In quantum field theory, the vacuum is not empty. It is a sea of virtual particle-antiparticle pairs that constantly pop into existence and annihilate each other, too briefly to be directly detected. But near the event horizon of a black hole, something special happens. A virtual particle-antiparticle pair can form with one particle just inside the horizon and one particle just outside. The particle inside the horizon falls inward. The particle outside the horizon can escape to infinity, becoming a real particle, carrying away real energy. And the energy for this comes from the mass of the black hole, which decreases. This process is real. It is not speculative. The mathematics is solid and the physical reasoning is well grounded. What is speculative is the exact nature of the information encoded in the Hawking radiation, which relates to the information paradox. But the existence of Hawking radiation itself, and the fact that black holes slowly evaporate through this process, is as well established as anything in quantum field theory in curved spacetime. The rate of evaporation is extraordinarily slow for large black holes. The luminosity of Hawking radiation from a black hole of mass m is proportional to 1 over m squared. The larger the black hole, the fainter the radiation. For the black hole at the center of the Milky Way, the Hawking luminosity is incomprehensibly faint, far below any conceivable detection threshold now or in the future. But given enough time, the evaporation proceeds. As a black hole evaporates, it gets smaller. As it gets smaller, its Hawking temperature rises and its luminosity increases. The process accelerates. The final stages of evaporation, when the black hole has been reduced to a Planck mass, are explosive. The remaining mass is released in a burst of radiation in a tiny fraction of a second, a final flash of energy from an object that has been cooling the universe for incomprehensibly long. What is emitted in this final burst? We do not know for certain, because the final stages of evaporation occur at Planck-scale energies, where quantum gravity effects are important and our current theories break down. But whatever is emitted, it carries the last of the black hole's mass energy out into the universe as radiation. And after that, there is nothing where the black hole was, just spacetime, healed, empty. The total energy emitted over the lifetime of a black hole is equal to its initial mass times the speed of light squared, by conservation of energy. The energy is spread out over an incomprehensibly long time, emitted at extremely low temperatures for most of the evaporation, and then released in a brief intense burst at the end. The universe eventually receives back all the energy that fell into the black hole, just in a completely different form and completely scrambled. After the last black hole evaporates, the universe contains only the products of Hawking evaporation: photons, electrons, positrons, neutrinos, and perhaps other light particles, all at extremely low energies spread through an unimaginably vast and expanding space. This is the beginning of the Dark Era, and the Dark Era just continues, and continues, and continues. The expansion of space carries the last particles further and further apart. The temperature of the universe continues to fall toward absolute zero, but never reaches it. Quantum fluctuations prevent a perfect zero-temperature state. The vacuum itself fluctuates, producing virtual particles that immediately vanish, but preventing the universe from ever being completely still. How long does the Dark Era last? In principle, forever, or at least for a time so long that the difference between very long and forever is not meaningful. If the dark energy continues to drive the expansion at its current rate or faster, the universe will expand without limit. Space will grow infinitely large. The surviving particles will be spread across infinite space. And as far as we can tell from our current physics, this process will go on indefinitely. Some cosmological models suggest that the dark energy might eventually change. If the dark energy density increases over time, the universe might end in a big rip, where the accelerating expansion eventually tears apart galaxies, then stars, then planets, then atoms, then subatomic particles, in a final catastrophic tearing of space itself. The Big Rip, if it occurs, would preempt the Dark Era entirely and end the universe in a violent singularity in the far future. But current observations are not consistent with a strong enough dark energy increase to cause a big rip in the near future, and many models do not predict it at all. Another possibility is that the dark energy is actually a cosmological constant, unchanging in time. In that case, the universe expands exponentially forever, and the Dark Era genuinely lasts without any defined endpoint. or the dark energy might eventually decrease, allowing gravity to eventually overcome the expansion and causing a big crunch, where the universe collapses back on itself in a time-reversed Big Bang. But again, current observations do not favor this outcome. The data points toward an eternal expansion. The most likely fate, based on what we currently know, is the one I have described. The universe expands forever, growing colder and emptier, with the last black holes eventually evaporating and the remaining particles spreading indefinitely through infinite space, in a state of permanent and deepening darkness. This is not a comfortable picture. It offers no renewal, no rebirth, no phoenix rising from the ashes. The universe, in the standard cosmological model, does not have a second act. What burns, burns once and is not rekindled. But I want to push back gently on the idea that this should be experienced as bleak, because the story of the universe is not primarily a story about its ending. It is a story about its middle. The Stelliferous Era, brief as it is in the cosmic context, is the most astonishing thing that has ever happened. Matter organized itself into structures of extraordinary complexity. Chemistry arose, biology arose, consciousness arose. Minds looked up at the sky and traced the arc of cosmic time from beginning to end. That is not the prelude to the story. That is the story. The Dark Era is the epilogue, long and quiet, and perhaps necessary in some thermodynamic sense, but not the point. The point is the 10 to the power of 14 years when the universe was alive with fire and chemistry, and apparently curiosity. We are in those years. We are the curiosity. The universe will not always be this interesting. Right now, in this brief window, it contains everything. Stars and planets and black holes and galaxies and life and minds and questions. In the future, it will contain less and less and less, until eventually it contains nothing but cold radiation in expanding space. But it contains all of this now, and we are here now, in this extraordinary window, watching the fires burn, asking where they are going, and understanding the answer. That seems worth something. That seems, in fact, worth everything. Sleep well tonight. The sun will rise tomorrow, as it has for 4.5 billion years. The stars will still be there when the sky darkens. The universe is 10 to the power of 10 years old and still burning, still making new stars, still supporting chemistry and biology and consciousness. We are in the brief, brilliant, improbable middle of the greatest story ever told. Good night. Let me go back and spend more time in the Stelliferous Era, because it is where we live, and it deserves a richer picture than I have given it so far. The Stelliferous Era is not a single uniform period. It has its own internal structure, its own arc. We are living through the declining phase of a peak that occurred about 10 billion years ago. The universe's star formation rate peaked when the universe was roughly 4 billion years old. At that time, galaxies across the observable universe were forming stars at a rate perhaps 10 times higher than they are today. The night sky, if you could have seen it then, would have been brighter and bluer, filled with young hot stars blazing with the fierce light of a universe in the full flush of its most productive era. Since that peak, the rate has been declining. The universe has been using up its reserves of cold hydrogen gas, the raw material of star formation. As that gas is consumed, converted into stars, processed through stellar evolution and returned as enriched gas, but not in sufficient quantities to maintain the peak formation rate, the overall star formation rate has been declining. We are living in the long, slow decline. By the time of the last red dwarfs, star formation will have essentially ceased for trillions of years. The last stars forming will be in the most gas-rich environments, the most isolated pockets of cold hydrogen that manage to avoid incorporation into stars during the productive early era. They will be small, dim, long-lived stars burning slowly in the dark, outlasting all their predecessors by an enormous margin. The most massive stars that have ever existed or will ever exist burned in the very early universe. Stars formed from essentially pure hydrogen and helium, with no heavy elements, are called population III stars. They are theorized to have been very massive, perhaps hundreds of times the mass of the Sun, because in the absence of metals, which are elements heavier than helium in astronomical parlance, the gas clouds that form stars cannot cool as efficiently and tend to form larger, hotter objects. These population III stars burned briefly and brilliantly, lived for perhaps 1 million years, and died in supernovae or direct collapse to black holes, seeding the universe with the first heavy elements. We have never directly observed a population III star. They are too old and too far away. But the James Webb Space Telescope is searching for their signatures, looking at the very earliest galaxies to find evidence of their influence. The spectral signatures of galaxies with unusual elemental abundances, or even direct detection of individual very massive stars in the earliest cosmic epochs, could provide our first direct glimpse of these ancient fires. After population III stars came population II stars, formed from gas that had been enriched by the first supernova explosions. These stars are older and lower in metals, found today in the oldest parts of galaxies, in globular clusters, and in the galactic halo. Many of them are still burning today, ancient and metal-poor, witnesses to the universe's earliest epochs. And after them came population I stars, like our Sun, formed from gas that has been processed through many generations of stars and is rich in heavy elements. The progression from population III to population II to population I is the progression of chemical enrichment in the universe. Each generation of stars enriches the interstellar medium with heavy elements, making the next generation more chemically complex. The Sun is a third or fourth generation star, formed from gas that has been through multiple cycles of stellar birth and death. The heavy elements in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, were all forged in stars that lived and died before the Sun was born. This chemical enrichment is part of what makes the Stelliferous Era so remarkable. It is not just the era of stars. It is the era of chemistry. Heavy elements produced by stellar nucleosynthesis and distributed by supernova explosions make possible the chemistry of planets, the chemistry of life. Without the Stelliferous Era's billion-year program of nuclear cooking and supernova seeding, there would be no rocky planets, no liquid water, no organic molecules, no biology. The Stelliferous Era made us possible, not just by producing the sun that warms our planet, but by producing every heavy atom in every molecule in every living thing. We are, in the most literal sense, products of the Stelliferous Era, assembled from its waste products, animated by its energy. And the Stelliferous Era is finite. It has a beginning, a middle we are living through, and an end. The end is not a catastrophe. It is just the last fires going out, the last red dwarf cooling to darkness. But it means that the chemistry of life, which depends on stars and their energy and their nucleosynthesis, is possible only in this window. If intelligence arose elsewhere in the universe, as it may have, it arose in the Stelliferous Era. If it arises in the future, It will also arise in the Stelliferous Era, for there is no other era hospitable to it. The entire domain of possible intelligent life in the universe is bounded by the start and end of stellar activity. And we are somewhere in that domain, in the middle of the Stelliferous Era, in what is probably not the last chapter of possible intelligent life, but certainly not the first. Now let me talk about something that connects the end of the universe to one of the deepest questions in physics, the question of entropy. Entropy is a measure of disorder, or more precisely, of the number of possible microscopic states that correspond to a given macroscopic state. High entropy means many possible arrangements. Low entropy means few possible arrangements. The second law of thermodynamics says that entropy in a closed system tends to increase over time. Things tend toward disorder, not order. The universe began in an extraordinarily low entropy state. The Big Bang produced a universe of remarkable uniformity, almost perfectly smooth, with only tiny fluctuations. This extreme uniformity is actually an extremely low entropy configuration, because the vastly more numerous possible arrangements of the same matter and energy would be much less smooth, much more clustered, much more disordered. Why the universe began in such a low entropy state is one of the deepest unsolved problems in physics. Over the history of the universe, entropy has been increasing. Stars form from clouds of gas, creating local pockets of low entropy, but the radiation they emit into space more than compensates, ensuring that the total entropy of the universe increases. Galaxies form, creating gravitational structure, but the heat and radiation produced in the process increase the total entropy. Every process, every reaction, every event in the universe increases the total entropy. The ultimate fate of the universe is a state of maximum entropy. This is sometimes called the heat death of the universe, a term coined in the 19th century by the physicist William Thomson, Lord Kelvin, who recognized that the second law of thermodynamics implied a final state of uniform temperature and maximum disorder from which no further work could be extracted. In the Dark Era, the universe approaches this state of maximum entropy. The temperature is nearly zero. The matter is maximally dispersed. There are no gradients, no temperature differences, no free energy available to drive any process. Everything is as disordered and as spread out as it can be. The universe has run down. This is the thermodynamic endpoint, and it is consistent with everything else I have described about the Dark Era. The two pictures, the astronomical picture of cooling and dispersal and the thermodynamic picture of maximum entropy, converge on the same final state, but there is a subtlety that is worth noting. Maximum entropy in a universe with dark energy is not the same as maximum entropy in a static universe. The expanding universe has a growing maximum entropy because there is more and more space for matter and energy to fill. The universe is always approaching, but never reaching its maximum entropy, because that maximum is always growing. This is one of the reasons the Dark Era can last so long without settling into a truly final state. There is also a subtle quantum mechanical effect called a Poincaré recurrence. In a finite system in a finite volume of space, the Boltzmann H theorem, combined with the quantum mechanical discreteness of states, implies that any system will eventually return arbitrarily close to any previous state, given enough time. For the universe, this would imply that the current configuration, or any previous configuration, would eventually recur in some incredibly distant future. The timescale for a Poincaré recurrence of the entire observable universe is incomprehensibly large. Something like 10 to the power of 10 to the power of 100 years, a number so large it makes the entire timeline we have discussed tonight look like nothing. And in a universe with dark energy and eternal expansion, where the accessible volume of space is limited by the cosmological horizon, the applicability of Poincaré recurrence is disputed. But the idea that the universe might, given truly infinite time, spontaneously fluctuate back into a state of low entropy and begin again is a genuine physical possibility that some cosmologists take seriously. This would not be a rebirth in any conventional sense. It would be a quantum fluctuation, not a new Big Bang with a new inflationary expansion. And the timescales involved are so vast that the question of whether the universe has sufficient time for such a fluctuation depends on whether the dark era is truly eternal, which depends on the nature of dark energy. If dark energy is a cosmological constant, the universe is effectively eternal, and Poincaré recurrences can in principle occur. If the universe ends in a big rip or some other finite-time catastrophe, they cannot. We do not know which scenario is correct. We are working to find out by studying the properties of dark energy with increasing precision. The answer to whether the universe is truly eternal or has a definite end may be within reach of future cosmological observations. Let me spend a little more time on something that I think is one of the most profound aspects of the story of the universe's end. It is the question of what happens to information. Throughout the history of the universe, information is being created and organized and destroyed. A star forms from a diffuse gas cloud, and information about the specific arrangement of atoms in that gas is encoded in the star's structure. A planet forms with a specific geological and chemical history. A genome evolves, encoding the information of adaptation to an environment. A mind develops, encoding the information of experience and knowledge. All of this information is, in a sense, temporary. The star will die. The planet will be sterilized or destroyed. The genome will eventually be lost. The mind will cease, but where does the information go? In classical physics, information is conserved. The laws of physics are time reversible, at least in principle. If you knew the exact state of every particle in the universe, you could run the laws backward and recover any past state. Information is never truly destroyed. It just becomes harder and harder to access as it gets mixed and scrambled. In quantum mechanics, the situation is more subtle. The information paradox in black hole physics asks whether information is truly destroyed when things fall into black holes, or whether it is preserved in the Hawking radiation, albeit in incredibly scrambled form. Current theoretical work suggests it is preserved, but the mechanism is not fully understood. In the dark era, the information encoded in stars, planets, genomes, and minds has been dispersed and scrambled by the processes of the Stelliferous, Degenerate, and black hole eras. It is still there in principle, encoded in the positions and momenta of the photons and particles filling the expanding universe. But it is so thoroughly mixed, so irreversibly scrambled, that no physical process could ever reconstruct it. The memories are gone. Not destroyed in a strict physical sense, perhaps, but inaccessible in any meaningful sense forever. The Dark Era universe carries the ghost of all that has happened, encoded in the thermal noise of its background radiation, but that encoding is beyond any possible reading. This is a kind of loss that is hard to articulate. The universe forgets. Not in the poetic sense of failing to remember, in the physical sense of dispersing the information that constituted memory into forms that are permanently unreadable. The history of the Stelliferous Era, the birth and death of stars, the evolution of life on 1 trillion planets, the thoughts and dreams and discoveries of whatever minds arose during those billions of years, all of it is encrypted into the background radiation of the Dark Era, readable by no one, preserved in principle but lost in practice forever. That is the ultimate thermodynamic fate of all information, and there is something sobering about it, not just sad but genuinely profound. The universe is a place where information can arise and organize and complexify briefly, and then disperse into irreversible noise. The brief window of complexity, the era we are in, is bounded on both ends by chaos and disorder. Before the Big Bang, as far as we know, there was no ordered information. After the Dark Era, ordered information will never arise again. We are in the window. And knowing that we are in the window, knowing the full arc of cosmic time from Big Bang to heat death, is itself a remarkable piece of organized information. It is the universe briefly understanding its own fate through the minds it produced in the Stelliferous Era. That understanding is not nothing. It may, in fact, be the most extraordinary thing that has ever happened. Sleep well tonight. The universe is still here, still burning, still making stars and galaxies and chemical reactions and whatever else complexity the Stelliferous Era produces. The heat death is real and it is coming, on timescales so vast they make all of human history look like a single moment. But right now, tonight, the universe is alive with fire, and you are part of it. Good night. Let me take you through the timeline one more time, but this time with more attention to the specific numbers, because the numbers in this story are not just large. They are incomprehensible in a way that deserves to be confronted directly. The universe is currently about 8 billion years old. That is 138 times 10 to the power of 10 years. On a logarithmic scale, we are at about log 10 of 10. For the rest of this section, I am going to use a notation where I give you the exponent directly. We are at year 10 to the 10. The sun will exhaust its hydrogen fuel in about 5 billion years, or 10 to the 7 years from now. We are close to the sun's midpoint of life. Afterward, the red giant phase, the planetary nebula, the white dwarf. The sun as a luminous star will be finished in roughly 5 to 6 billion years from now. The last sun-like stars in the Milky Way will have died by about 10 to the 12 years from now, roughly 100 times the current age of the universe. At that point, only low-mass red dwarfs remain as active stars. The Milky Way will have reddened to near invisibility, lit only by the dim glow of these ancient stellar embers. The last red dwarfs will have exhausted their hydrogen by about 10 to the 13 or 10 to the 14 years from now, 1 to 10 trillion years from now. This is the end of the Stelliferous Era in our galaxy. The sky goes dark. By 10 to the 19 years from now, the gravitational evaporation of galaxies will have largely dissolved their stellar structures. The individual remnants, white dwarfs, neutron stars, and black holes, will have been scattered into intergalactic space by the accumulated gravitational interactions over these immense timescales. The Milky Way will no longer exist as a recognizable structure. Its remnants will be dispersed across a vast region of space. If proton decay occurs, as grand unified theories predict, it will be significant by around 10 to the 33 to 10 to the 40 years. all the ordinary matter in the universe, every white dwarf, every neutron star, every cold rocky planet, every molecule will have decayed by around 10 to the 40 years. The universe will contain no atoms, no nuclei, no protons. Only electrons, positrons, photons, neutrinos, and black holes. The black holes themselves, accreting nothing in the empty universe, will be evaporating through Hawking radiation. Stellar mass black holes, those between roughly 5 and 100 solar masses, will have evaporated by around 10 to the 77 years. The more massive black holes, those at the centers of former galaxies, take longer. A billion solar mass black hole takes about 10 to the 96 years. The most massive black holes known, those of tens of billions of solar masses, take up to 10 to the 100 years to evaporate. By 10 to the 100 years from now, roughly, all black holes in the observable universe will have evaporated. The universe contains only the products of Hawking evaporation, plus any remaining leptons that have not annihilated, plus photons and neutrinos, all in a universe that has expanded by a factor many orders of magnitude larger than its current size. And then the dark era continues. For how long, we do not know, perhaps forever. The expansion continues. The temperature falls. The universe grows emptier and darker and colder. These numbers 10 to the 77, 10 to the 100 are not arbitrary. They follow from physics we can calculate. The Hawking evaporation time follows from the equations of quantum field theory in curved spacetime. The proton decay lifetime follows from the coupling constants of grand unified theories. These are not guesses. They are the outputs of the best theories we have, applied to scenarios we cannot directly observe. The range of uncertainty is large, because we do not have a confirmed grand unified theory, and because the evaporation time depends sensitively on the mass of the black hole. But the structure of the timeline, the sequence of eras and the approximate timescales is as robust as any prediction we can make in cosmology. Now let me talk about something that is sometimes overlooked in discussions of the far future universe: the role of dark matter. We know that dark matter makes up about 27% of the total energy content of the universe, compared to about 5% for ordinary matter. Dark matter does not interact electromagnetically. It does not emit light. It does not form atoms or molecules. In the current universe, it plays a crucial gravitational role, providing the framework within which ordinary matter collapses to form galaxies and stars. But what happens to dark matter in the far future? The answer depends on what dark matter is, which we do not yet know. If dark matter consists of heavy particles that can annihilate with each other, as some models predict, then over very long timescales, dark matter particles will occasionally encounter each other and annihilate, releasing energy. In dense dark matter environments, this process could sustain a faint energy output long after all the stars have gone dark. Some researchers have speculated that, in the far future, dark matter annihilation might power extremely exotic versions of stars, clumps of dark matter dense enough that the annihilation energy exceeds the rate of energy loss, creating stable, long-lived objects. But this depends entirely on the nature of dark matter and is highly speculative. If dark matter does not annihilate and does not decay, it will persist through all the eras we have discussed. It will outlast the stars, outlast the white dwarfs, potentially outlast even the black holes if it is truly stable. In the dark era, the universe will contain not just a faint sea of photons and electrons, but also a more diffuse sea of dark matter particles spread throughout the expanding universe. These dark matter particles will exert gravitational effects on each other and on the baryonic matter around them. But in the dark era, when densities are so low and separations so vast, these gravitational effects will be negligible for practical purposes. The dark matter will simply drift along with the expansion of space, growing ever more dilute, ever more isolated, ever more separated from any other particle. The Dark Era universe, with its dark matter background, its photon background, its neutrino background, and its occasional electrons and positrons, is an almost featureless sea of particles and radiation, expanding without bound, growing colder and emptier without limit. It is the universe stripped of everything that made it interesting, everything that made it remarkable, everything that made it, in any meaningful sense, alive. And yet it persists. The laws of physics do not require the universe to end. They do not require a final state. The Dark Era can continue indefinitely. The universe does not have to stop. It just has to become emptier and colder and darker forever. This is, in some ways, the most unsettling aspect of the whole story. Not that the universe ends dramatically in a final catastrophe, but that it fades gradually into something barely distinguishable from nothing and then continues fading indefinitely. No final moment, no last event, just an asymptotic approach to emptiness that never quite arrives, or almost never. Because there is one final process worth mentioning, one that occurs on timescales so vast that they make everything else in this story look brief. It is the random fluctuation of vacuum energy that could, in principle, nucleate a new Big Bang. In quantum field theory, the vacuum is not perfectly stable. It is subject to quantum fluctuations. On very small scales and very short timescales, these fluctuations are constant and ubiquitous, the virtual particle pairs we mentioned in the context of Hawking radiation. But on cosmic scales and cosmic timescales, very rare large fluctuations are possible. One class of these fluctuations is the spontaneous nucleation of a new inflationary bubble, a new universe, within the expanding Dark Era universe. If the dark energy that drives the expansion is itself a quantum field, which is possible, then fluctuations of that field could occasionally push a tiny region into a state of high energy density, which would then inflate, creating a new universe inside the old one. The timescale for this is so vast that it makes even the Poincaré recurrence timescale seem brief. We are talking about something like 10 to the power of 10 to the power of 10 to the power of 10 years. Numbers nested inside numbers nested inside numbers, each one already incomprehensibly large. These are not numbers in any practical sense. They are mathematical objects that describe the theoretical possibility space of the universe, not timescales on which anything we could call an observer could wait. But the possibility exists. In an eternal universe with eternal time, even the rarest fluctuations eventually occur. A new universe could nucleate in the Dark Era void, a new Big Bang, a new inflation, a new Stelliferous Era, new stars and planets, and potentially new minds. Not as a recurrence of our universe, but as a genuinely new beginning with different initial conditions and potentially different physical constants. This is the multiverse idea, expressed in temporal rather than spatial terms. Not other universes existing now, alongside ours, but other universes arising in our future, nucleated from the quantum vacuum of our Dark Era, beginning their own journeys through their own stelliferous eras and beyond. Whether this actually happens, whether the universe produces new big bangs in its dark era, depends on the detailed properties of the vacuum and the dark energy, which we do not fully understand. But it is a genuine physical possibility, not a fantasy. And it gives the story of the universe's end a different character than a simple fade to black. Perhaps the universe does not end. Perhaps it transforms. The Stelliferous Era gives way to the Degenerate Era, which gives way to the Black Hole Era, which gives way to the Dark Era, which occasionally and over incomprehensible timescales gives rise to new universes, new stelliferous eras, new opportunities for complexity and life and minds. This is a more hopeful picture than simple heat death, but it is important to be honest about the uncertainty. We do not know if new universes nucleate from the Dark Era vacuum. We do not know if they would be anything like ours, or if they would be habitable, or if they would produce minds. These are speculations, well motivated by physics but not confirmed. What is confirmed is the timeline from here to the Dark Era. The stelliferous, degenerate, black hole eras are predicted by well-tested physics and cannot be avoided unless our current understanding is badly wrong in ways we have no current reason to suspect. And what is not confirmed, but possible, is what happens after. Whether the Dark Era is truly the end or merely the latest and longest chapter in an ongoing cosmic story. We are, in either case, in the brief, brilliant window of the Stelliferous Era. That does not change. Our universe is burning now, and it will stop burning eventually, and what comes after is slow and dark and cold. Whether anything comes after that, whether the story continues in some form, is something we are working to understand. The question itself is remarkable. That we can ask it, that we have developed the physics to trace the fate of the universe from here to the heat death and beyond, that we live in the moment when this knowledge is within human reach, is extraordinary. We are the brief flowering of the universe's capacity for self-understanding. We are the moment when the universe knows where it is going. That is worth sitting with. Sleep well. The universe is still young by the standards of its full story. The Stelliferous Era has billions of years left. The sun will burn for 5 billion more years. The last stars will burn for trillions. And then the long dark will begin and continue and perhaps never end. But right now it is bright, and you are here to see it. Good night. I want to go deeper into something that is central to this story, but rarely explained properly. The relationship between the expansion of the universe, dark energy, and what physicists call the cosmological event horizon. Right now, the observable universe extends about 46 billion light-years in every direction. This is the distance light has been able to travel to us since the Big Bang, accounting for the expansion of space that has occurred during transit. But the observable universe is not a fixed thing. It changes over time, and the way it changes in the future reveals something important about the ultimate isolation of the Dark Era. If the universe were not accelerating in its expansion, the observable universe would grow over time. More and more regions of space would come within our observational reach, as light from increasingly distant regions finally had enough time to travel to us. The universe would become, in a sense, more accessible over time. But we live in a universe dominated by dark energy, which causes the expansion to accelerate. And in an accelerating universe, the opposite happens. The most distant galaxies we can currently observe are being carried away from us by the expansion faster than light can travel toward us. Not because they are moving through space at superluminal speeds, but because the space between us and them is expanding, and for the most distant galaxies, the rate of that expansion exceeds the speed of light. This means that the light those distant galaxies emit right now, today, will never reach us. It will be emitted, travel toward us at the speed of light, but the space between it and us will expand faster than it can cross. That light will never arrive. We are already receiving the last light that will ever reach us from the most distant observable galaxies. Their future is permanently hidden from us. This is the cosmological event horizon. In an accelerating universe, every observer is surrounded by a horizon beyond which they can never receive any information. This horizon is not at a fixed distance. It is at the distance where the recession speed due to the expansion equals the speed of light. In our universe, this is currently about 16 billion light-years away. As time passes, the galaxies we can currently see will recede past this horizon. Their light will be redshifted to longer and longer wavelengths, stretched and dimmed by the expansion, until it fades below any possible detection threshold. The number of galaxies in our observable universe will decrease over time, not increase. In the far future, after hundreds of billions or trillions of years, the only galaxy we will still be able to observe will be our own, or rather the merged remnant of the Milky Way and Andromeda. All other galaxies will have receded beyond the cosmological event horizon, redshifted to invisibility. An observer in the far future, equipped with the best conceivable telescopes, would see only the local group in an otherwise dark sky. Every other galaxy in the universe, all 2 trillion of them, would be gone, not because they ceased to exist, but because the universe has carried them beyond the reach of light. This is a form of cosmic loneliness that is rarely discussed but deeply profound. The universe is becoming more isolated over time. The local group is our future, and beyond the local group, an expanding void of darkness. This isolation becomes complete long before the Stelliferous Era ends. By the time the last stars are dying, the only stars visible will be within the gravitationally bound structure of the local group, everything else having long since vanished beyond the event horizon. The Dark Era universe, in addition to being empty of matter and energy, will also be irreversibly fragmented. Whatever remains in different regions of space will never be able to exchange information or energy. The Dark Era is not just dark, it is divided, disconnected, each particle drifting in its own private expanding universe, separated from every other particle by a gulf of expanding space that light can never fully cross. This ultimate isolation is, I think, one of the most poignant aspects of the universe's fate. It begins connected. The early universe is dense and hot, and every part of it is in contact with every other part. Then it expands and structures form and galaxies separate, and over time the connections thin. And eventually, in the Dark Era, every particle is its own universe, bounded by its own horizon, forever isolated from everything else. The universe goes from total connection to total disconnection, and the Stelliferous Era is the brief middle period when there is enough connectivity, enough proximity between stars and planets and chemical systems for complexity to arise. Now let me take you through the specific fate of our galaxy, the Milky Way, in more detail. Because our galaxy has a specific future that is different from the average galaxy, and understanding it personalizes the cosmic story in a way that is worth doing. The Milky Way and the Andromeda galaxy are currently on a collision course. They are approaching each other at about 110 kilometers per second. In about 4 to 5 billion years, they will collide. The collision will not be the dramatic crash you might imagine, because galaxies are mostly empty space and the individual stars are unlikely to directly collide. But the gravitational interaction will be enormous, scrambling the orbits of stars, triggering massive bursts of new star formation from the colliding gas clouds. And ultimately, after perhaps 1 billion years of interacting, merging the two galaxies into a single giant elliptical galaxy. This merged galaxy is sometimes called Milkomeda. It will be a rounder, puffier structure than either of its progenitors, with the spiral arms dissolved and the stars in more random orbits. The central black holes of the two galaxies, Sagittarius A star with 4 million solar masses, and the Andromeda black hole with roughly 100 million solar masses, will eventually spiral together and merge into a more massive black hole at the center of Milkomeda. The merger will trigger a burst of star formation from the shocked and compressed gas clouds, but it will also consume a significant fraction of the galaxy's gas supplies, leaving less for future star formation. After the merger, Milkomeda will be a galaxy with a declining star formation rate, gradually using up its remaining gas reserves and producing fewer and fewer new stars. Several other smaller galaxies in the local group will also merge with Milkomeda over the following billions of years. The Large and Small Magellanic Clouds, currently orbiting the Milky Way as satellite galaxies, will be absorbed within a few billion years. Other dwarf galaxies of the local group will be drawn in by Milkomeda's gravity over longer timescales. Eventually, Milkomeda will be all that is left of the local group. All the smaller galaxies will have been absorbed, and all the more distant galaxies will have receded beyond the cosmological event horizon. Milkomeda will be the only galaxy visible in the sky, surrounded by a dark void of expanding space. As the Stelliferous Era draws to a close, Milkomeda's stars will be dying, one by one, the most massive first and the red dwarfs last. The galaxy will dim from a bright combination of blue, white, yellow, orange, and red stars to a collection of cooling white dwarfs and dim red stars to, ultimately, darkness. The last red dwarf in Milkomeda will burn out sometime around 10 to the 14 years from now, and then even the merged local group remnant will go dark. The supermassive black hole at the center of Milkomeda will persist long after the stars have died, growing slowly by accreting whatever stray matter drifts near it, cooling the surrounding region by emitting occasional bursts of radiation. It will be the most massive and long-lived object in the former local group. Eventually, it too will begin to lose mass to Hawking radiation, on timescales of 10 to the 96 years or more. And ultimately it will evaporate, the last event of any significance in the region of space that once contained our galaxy. After that, the region of space that contains the local group's remnants will be indistinguishable from any other region of the Dark Era universe, a diffuse sea of photons and occasional particles, expanding without limit in a universe that has long since ceased to be interesting in any conventional sense. This is where we are going. This is the fate of the Milky Way, of the Sun, of Earth, of everything we have ever known or will ever know. It is a fate measured in timescales so vast that the entire history of human civilization is a rounding error on the first term of the first era. It is a fate that follows inexorably from the laws of physics that we can trace forward from here with reasonable confidence, that awaits not just us but every star, every galaxy, every black hole in the observable universe. And yet here we are at the beginning of this story, in the brief, brilliant window when the universe is young and full of fire. The Milky Way is still forming new stars. New planets are being born. New chances for chemistry and life and minds are arising right now, in the stellar nurseries of the galaxy, in the collapsing gas clouds, in the young solar systems emerging from the dust. The Stelliferous Era is not over. It has billions of years to run. The sun will shine for another 5 billion years, enough time for civilizations to rise and fall 1,000 times if the history of Earth is any guide. And even after the sun dies, the red dwarfs will burn for trillions of years, cold and dim but burning, maintaining the conditions that could support whatever life is possible in their proximity. The end is real, but it is far away. And the middle, the burning, complex, chemically rich middle of the Stelliferous Era that we inhabit, is the most remarkable thing the universe has ever produced. Every star you see tonight is burning its hydrogen into helium, releasing energy, enriching the interstellar medium with heavy elements, potentially warming a planet somewhere in its habitable zone. Every star is a furnace of possibility. Every photon that reaches your eyes is carrying energy released by nuclear fusion in the heart of a star, energy that has been traveling for years or centuries or millennia to reach you in this moment. The universe is still giving, still burning, still making the conditions for complexity and life and minds. And those minds, at least the ones here on this planet at this moment in history, can trace the full arc of the story from Big Bang to heat death and find themselves, improbably and beautifully, in the middle of it. That is what tonight's journey was about, not the end really, the beginning and the middle, the places where the universe is alive, and the recognition, full and unambiguous, that we are in those places now. Sleep well. The universe will outlast us by incomprehensible margins. But right now, tonight, it is ours to observe and understand. Good night. Let me talk about something that bridges the physics of the universe's fate and our experience of time. It is the concept of the arrow of time, and it is deeply connected to the story of the universe's end. We experience time as flowing in one direction, from the past, which is fixed and inaccessible, to the future, which is open and undetermined. You can remember yesterday, but not tomorrow. You can affect the future, but not the past. Causes precede effects. This asymmetry of time, the arrow of time, is so fundamental to our experience that it is hard to imagine otherwise. But the fundamental laws of physics are, with a very small exception, time-symmetric. The equations of motion for particles, the equations of quantum mechanics, the equations of electromagnetism, all of these work equally well running forward in time or backward in time. If you filmed a process described by these laws and ran the film backward, the backward film would also describe a physically possible process. The laws do not intrinsically prefer one direction of time. The arrow of time that we experience is not encoded in the fundamental laws. It is a consequence of the initial conditions of the universe. The universe began in an extraordinarily low entropy state. As time progresses, the universe tends toward higher entropy states because there are vastly more high entropy states than low entropy states, and the laws of physics allow random transitions between states. Moving toward higher entropy is overwhelmingly likely, purely statistically, because high entropy states are so much more numerous. This means that the arrow of time, the feeling that time flows from past to future, from lower entropy to higher entropy, is a consequence of the fact that the universe started in a low entropy state. If you lived in a universe that was at maximum entropy, a universe in the Dark Era, there would be no arrow of time. All processes would be equally probable in both directions. There would be no memory, because memory requires a record, and making a record requires increasing the entropy of the recording medium, which requires a low entropy environment. There would be no causality in any conventional sense. There would be no experience of time flowing in any direction. The arrow of time is a gift of the early universe. It is a consequence of the Big Bang's low entropy initial state, and it will last only as long as the universe remains in a state significantly below its maximum entropy. During the Stelliferous Era, entropy is far from its maximum. The arrow of time is sharp and clear. But as the universe progresses through the Degenerate and black hole eras, entropy increases and the arrow becomes more ambiguous. In the Dark Era, entropy is so close to its maximum that the arrow of time effectively disappears. This has a strange implication. In the Dark Era universe, there is no meaningful sense in which time passes in a direction. There are quantum fluctuations, random transitions between states, but no preferred direction of change. The Dark Era is not just dark and cold and empty. It is, in a deep sense, timeless. This is not mysticism. It is the thermodynamic implication of maximum entropy. Without an entropy gradient, there is no arrow of time. Without an arrow of time, there is no meaningful sequence of events in the usual sense. The Dark Era is not a long sequence of moments leading somewhere. It is a nearly static state, punctuated by quantum fluctuations, with no direction, no narrative arc, no before and after in any experiential sense. Our experience of time, the sense that this moment follows from that moment and leads to the next, is a feature of the Stelliferous Era. It is made possible by the low entropy of the early universe and maintained by the processes of star formation and stellar evolution that continue to drive entropy upward in an orderly way. In the Dark Era, this experience would not be possible. Not because there are no observers, there are none, but because the physical conditions that make experience possible, that make memory and causality and the flow of time possible, are absent. We are, in this sense, creatures of the Stelliferous Era, not just biologically, but temporally. Our experience of time is a feature of the era we live in. The Dark Era universe does not just lack stars. It lacks the structure that makes the experience of time possible. This connects back to the idea of entropy and information I discussed earlier. Memory requires a record. Records require entropy gradients. Entropy gradients require a universe far from maximum entropy. We are far from maximum entropy now. We are so far from it that we have rich, detailed experiences of time and causality and memory. But the universe is moving toward maximum entropy, and as it does, the conditions for experience and for memory are being gradually eroded. By the Dark Era, those conditions are gone. The universe has used up its capacity for experience, not destroyed it in any dramatic sense, just used it up, consumed its store of orderly information, dispersed the entropy gradients that made experience possible, left a universe that is stable and long-lived, but incapable of anything like mind or memory or the experience of time. This is the full arc of the story. The universe begins in a state of extraordinarily low entropy. The Big Bang is, from a thermodynamic perspective, a moment of nearly perfect order. And from that ordered beginning, the universe moves inexorably toward disorder. The Stelliferous Era is the middle of this journey, the period when entropy is rising but still far from its maximum, when the entropy gradients are large enough to drive complex processes, including life and mind. We are the universe experiencing itself during the middle of its journey from order to disorder. We are a temporary eddy in the flow from low entropy to high. And knowing this, tracing the full arc from Big Bang to heat death, is the universe's brief capacity for self-understanding, made possible by the same entropy gradients that make all complex processes possible. That is a remarkable thing, not tragic, remarkable. Now let me spend a little more time on the specific physics of the Degenerate Era, because it contains one of the most extraordinary theoretical predictions in all of physics, the iron star. During the Degenerate Era, cold white dwarfs and neutron stars populate the dark remnants of former galaxies. These objects are stable, in the sense that they are not undergoing any significant energy-producing reactions, but they are not static. Over unimaginably long timescales, quantum mechanical tunneling allows even cold, stable objects to undergo structural changes. In particular, quantum tunneling allows the atoms in a white dwarf to rearrange themselves into more energetically favorable configurations. Carbon and oxygen atoms in a white dwarf are not in their lowest possible energy state. The lowest possible energy state of any collection of particles at zero temperature is the configuration that minimizes the total energy, which for a massive enough object means iron, the most stable nucleus in terms of binding energy per nucleon. Over timescales of around 10 to the power of 1500 years, quantum tunneling will cause the atoms in a white dwarf to gradually transform into iron. Not through nuclear fusion in the conventional sense, which requires high temperatures, but through quantum tunneling, which allows energy barriers to be crossed without the particle needing to have enough thermal energy to go over them. Given enough time, even cold objects can tunnel through energy barriers. The result is something called an iron star, a cold, dense sphere of iron, slightly smaller and denser than the original white dwarf, the product of billions of years of quantum tunneling rearrangements. Iron stars are not luminous. They emit no significant radiation. They are simply cold, dense balls of the most stable nuclear configuration, drifting in the dark. This prediction, the iron star, is one of the strangest and most specific in all of astrophysics. It follows from quantum mechanics and nuclear physics applied to conditions of extreme cold over extreme timescales. It has no observational test because the timescales are so vast, but the physics is solid. Given enough time, white dwarfs will become iron stars, and even after that, the story continues. Iron stars are more stable than white dwarfs, but they are not perfectly stable. Proton decay, if it occurs, will eventually disassemble even an iron star, converting its protons and neutrons into lighter particles and releasing energy. By 10 to the 40 years, assuming proton decay, even the iron stars are gone. If proton decay does not occur, iron stars persist through the black hole era. They are gradually eroded by Hawking radiation from the evaporating black holes around them, by the occasional impact of particles from the dark era background, and by continued quantum tunneling processes. Eventually, even without proton decay, quantum tunneling will convert an iron star into a black hole, on timescales of around 10 to the power of 10 to the power of 76 years. This is not proton decay. It is the entire iron star tunneling into a black hole configuration, a purely quantum mechanical process with no thermal driving. Given enough time, Matter simply rearranges itself into whatever configuration has the lowest energy. And for a sufficiently massive collection of matter, the lowest energy configuration is a black hole. These processes, iron stars and quantum tunneling to black holes, are the deepest consequences of quantum mechanics applied to the long-term fate of matter. They show that nothing is truly permanent. Even the most stable objects that seem like they could last forever, eventually transform on timescales governed by quantum mechanics. Stability is not permanence. It is just very slow change. The universe, over these incomprehensible timescales, is a universe of very slow change. Not nothing happening, not stasis, but change so slow that it makes geological timescales look instantaneous, change driven by the deepest and most subtle effects in quantum mechanics, producing outcomes that no classical physics could predict. And through all of it, the universe expands, space grows. The distances between things increase. The universe becomes more and more like nothing, asymptotically approaching emptiness without ever quite reaching it. This is the fate, and it is in its own way magnificent. The universe does not end in a moment. It ends in a process, an unimaginably long, gradual, inexorable process of cooling and dispersal and decay, governed by the deepest laws of physics, playing out on timescales that make the current age of the universe look like the first moment. We are at the first moment. We are in the universe's youth. And from this brief, bright, complex moment, we can trace the full arc of what comes after. The last stars will die. The galaxies will dissolve. The white dwarfs will cool and crystallize and tunnel to iron. The black holes will evaporate. The protons will decay. The universe will thin to a sea of photons and electrons. And then it will continue thinning, cooling, expanding, approaching nothing without ever arriving. That is the story. And it is our story because we are part of it. We are part of the brief, bright beginning, the complexity and life and mind that arose in the Stelliferous Era, the minds that could trace the full arc and understand where they stood within it. We are the universe at its most interesting, looking forward to its long, quiet end, grateful for the fire that still burns, aware of how rare and brief this burning moment is. Sleep well. The universe is still young. The Stelliferous Era still has billions of years to run. The stars are still burning. And we are still here at the beginning of the greatest story ever told. Good night. I want to spend some time now on a question that arises naturally from everything we have discussed. If the universe has such an extraordinary future of darkness and cold, why do we not see more evidence of that darkness right now? Why is the night sky dark? This seems like a trivial question. The night sky is dark because it is night. But there is a deeper puzzle here, one that was first articulated by the astronomer Heinrich Wilhelm Olbers in 1823. And that goes by the name Olbers' paradox. The paradox goes like this. If the universe is infinite and eternal, and if stars are distributed throughout it, then in every direction you look, your line of sight should eventually hit a star. Just as in a dense enough forest, every line of sight hits a tree eventually. If every line of sight hits a star, then the entire sky should be as bright as the surface of a star. The sky should be blindingly brilliant, uniformly lit by the accumulated light of infinite stars, but it is not. The night sky is dark, with stars appearing as isolated points of light against a black background. This is Olbers' paradox. Why is the sky dark? The modern resolution has two parts. First, the universe is not eternal. It has a finite age of 8 billion years, light from stars more than 13. 8 billion light-years away has not yet had time to reach us. so the number of stars whose light we can receive is finite, not infinite. Second, the universe is expanding. The light from distant stars is redshifted by the expansion of space, losing energy as it travels. The more distant the star, the more its light is redshifted, and the less energy it contributes to the sky brightness. These two factors together mean that the accumulated starlight does not add up to a bright sky. The finite age of the universe and the expansion of space conspire to make the sky dark. But here is the connection to the universe's fate. The darkness of the night sky is not a permanent feature of the universe's history. In the very early universe, before the first stars formed, the sky was bright, not with starlight, but with the hot plasma of the early universe itself, glowing in all directions. Then, as the universe cooled and the plasma became transparent, the sky went dark and has remained dark through the Stelliferous Era, lit only by the discrete points of light from individual stars. As the Stelliferous Era ends and stars go out one by one, the night sky will become darker still. In the Degenerate Era, the sky will be essentially black, with only the faint glow of cooling white dwarfs providing any light. In the Dark Era, the sky will be completely dark to any optical instrument, with only extreme wavelength photons providing any radiation at all, so redshifted by the expansion of space that they are essentially undetectable. The dark sky we see tonight, beautiful and star-filled as it is the most luminous the sky will ever be again. The universe's sky has been getting darker since the peak of star formation 10 billion years ago, and it will continue getting darker for the remaining trillions of years of the Stelliferous Era, and darker still through the subsequent eras, until in the Dark Era it reaches a darkness that makes our darkest nights look blazingly bright by comparison. This is another way of understanding our privileged position in cosmic time. We live in the era of starlight. The era when the sky, when viewed from a planet orbiting a quiet star far from the galactic center, is dark but full of light, full of stars and galaxies and nebulae, and the faint background glow of the cosmic microwave background. A sky rich with information about the history of the universe and the structure of matter and the physics of stars and the distribution of galaxies. A sky that tells a story if you know how to read it. In the future, the sky will tell no story. It will be dark and empty and silent, providing no information about anything because there will be nothing left to provide information. We are in the era of the readable sky, and we are reading it. Now let me talk about one more thing. The way the universe's fate connects to the deepest questions in fundamental physics, specifically to the question of why the universe exists at all. The universe, from the Big Bang through the Stelliferous Era, is a structure of extraordinary order that is gradually becoming disorder. The second law of thermodynamics ensures this. But the second law raises an immediate question. Where did the initial order come from? Why did the universe begin in such an extraordinarily low entropy state? This is not a question that current physics answers. The Big Bang singularity, the moment of zero time, is a place where our equations break down. We cannot calculate what happened there or before there using current physics. We do not know why the universe began in the specific low entropy state it did. We do not know if it began in that state by chance, by necessity, by design, or by some process we have not yet understood. The universe's fate, the heat-death, does not answer this question, but it does provide a boundary condition that makes the question more precise. The universe began in a low entropy state. It will end in a high entropy state. The Stelliferous Era, the era of stars and life and minds, is the middle of this journey. Whatever the ultimate explanation for the universe's initial conditions, it must explain why those conditions were so extraordinarily ordered, so precisely arranged for the long, rich journey from low entropy to high entropy that has produced everything we know. Some cosmological models suggest that the initial low entropy is not a mystery, but an inevitability. If the universe is eternal, and if universes can nucleate from vacuum fluctuations, then most nucleated universes will be small and short-lived, with minimal complexity. Our universe, with its long, rich Stelliferous Era and its capacity for life and minds, would be an unusually large and long-lived fluctuation, selected by the anthropic consideration that only such large, long-lived universes can contain minds to observe them. But this argument, like all anthropic arguments, is contested. Whether it explains the initial low entropy or merely reframes the question is a matter of ongoing debate. What is not contested is the phenomenological description. The universe began ordered. It is becoming disordered. The journey from order to disorder, across the immense timescales we have been discussing tonight, is one of the most fundamental physical processes in the cosmos. And we are writing it here in the middle of the Stelliferous Era, watching it happen, understanding it. That understanding is itself an extraordinary outcome of the process. The entropy gradient that drives the flow from order to disorder is also what makes minds possible. Minds are dissipative structures, maintained by the flow of energy from low entropy sources to high entropy sinks. The sun is our low entropy source. The cold night sky is our high entropy sink. The flow of energy from sun to sky through the Earth's biosphere maintains the order that constitutes life and mind. We are thermodynamic eddies in the flow from order to disorder. We exist because the universe is not yet at maximum entropy. We think because the entropy gradient that maintains our existence is still large enough to support the complex processes of thought. And we understand the universe because those same processes of thought have proven capable of modeling the physical laws that govern the whole. The universe made minds that can understand where the universe is going. That is, from any reasonable perspective, remarkable. And now let me bring this full circle, back to the very beginning. Back to the question of what happens before the Dark Era, and specifically to the question of what happens at the very end of the Stelliferous Era, when the last star dies. The last star to die will not be a spectacular death. It will not be a supernova. It will not produce a neutron star or a black hole. The last star will be a small red dwarf, burning so slowly and so completely that it will consume nearly all of its hydrogen before running out of fuel. Unlike more massive stars, which develop layered structures and eventually exhaust their fuel before it can all be consumed, the lowest mass red dwarfs are fully convective. They circulate all of their material through the core, burning all of their hydrogen before the end. When the last red dwarf exhausts its fuel, after trillions of years of burning, it will contract and cool, becoming a white dwarf. A small, dense, cooling remnant of carbon and oxygen. It will not expand into a red giant. It will not shed a planetary nebula. It will simply fade. The nuclear fires that have sustained it for trillions of years will go out, and it will cool toward darkness. This last dying star will be in some galaxy, perhaps in a cluster, perhaps isolated, perhaps a distant descendant of the Milky Way or Andromeda, or some other galaxy that survived the mergers and dissolutions of the early eras. It will be dim and red, and barely distinguishable from the faint glow of the older white dwarfs around it. Its death will be quiet, marked only by a gradual dimming that would be imperceptible on human timescales. But it will be the last. After it, no new stars will form. No new sources of light will arise in the universe through stellar processes. The Stelliferous Era will be over, and the long dark of the Degenerate Era will begin. That moment, the death of the last star, is perhaps the most significant moment in the future of the universe. Not the most dramatic, not the most energetic, but the most meaningful in the sense of marking a transition. The universe before that moment contains fire. The universe after that moment does not. The boundary between the Stelliferous Era and the Degenerate Era is the boundary between a universe that can support life and a universe that cannot, at least not in any form we can currently imagine. We are on the Stelliferous side of that boundary. We will always have been on the Stelliferous side of that boundary. The question of what happens to life and mind as the Stelliferous Era ends is one we cannot fully answer. Perhaps life adapts, finds ways to harvest the faint energy of cooling white dwarfs or the hawking radiation of black holes, extends itself into the degenerate and black hole eras on timescales we cannot imagine. Perhaps it does not. Perhaps the death of the last star is also the death of the last mind. We do not know, and the uncertainty is appropriate because the future is open and the ingenuity of life, wherever it exists, is not something we can fully predict from here. What we can say is that the Stelliferous Era is the era of possibility. While stars burn, energy is available. While energy is available, complexity can be maintained. While complexity can be maintained, life and mind can arise and persist. The Stelliferous Era is the window for everything we consider valuable in the universe. That window is open now. It will remain open for a long time by human standards, but it will close. The universe does not burn forever. And knowing this, really knowing it, changes how you see the night sky. The stars are not eternal. They are burning now. They are a temporary feature of a universe in transition, converting the low entropy of their nuclear fuel into the high entropy of their radiation, doing it beautifully, doing it for billions of years, but doing it in a way that must eventually end. Every photon from a star is a receipt from the universe's energy account, and the account is being drawn down, star by star, year by year, across the long arc of the Stelliferous Era. We are here during the drawing down. We are part of the complexity that the drawing down produced, and we are watching, with wonder and precision, the process that will eventually end. That seems like the right response. Wonder and precision together. Amazement at being here, at being part of this, at having the capacity to understand it. And precision in what we actually know, in how we describe the physics, in how we distinguish what the science says from what we project onto it. The universe will end in cold and dark. That is physics. The universe is magnificent in its present burning state. That is also physics. We are here in the burning state, able to understand both the burning and the cold that follows. That is the remarkable situation we find ourselves in. Sleep well. Somewhere in the Milky Way right now, a star is being born. Somewhere else, a star is dying in a supernova explosion, scattering heavy elements into the interstellar medium. Somewhere, a planet is cooling from a molten state, developing an atmosphere, perhaps providing conditions for chemistry. And somewhere, perhaps, another mind is looking up at its own night sky, asking the same questions we are asking, tracing the same arc of cosmic time, finding itself in the same extraordinary position of being alive and curious in the brief, brilliant middle of the universe's story. The Stelliferous Era is not over. Good night. Let me close with a meditation on timescales that I hope will leave you with the right sense of perspective. Not despair, not false comfort, but genuine perspective on where we are in the story of the universe. The age of the observable universe is 13.8 billion years. In the notation I have been using, that is 10 to the 10 years. The number 10 is 10 to the 1, 100 is 10 to the 2, 1 million is 10 to the 6, 1 billion is 10 to the 9. The age of the universe is 10 to the 10 roughly. The age of the Earth is 4.5 billion years, or 10 to the 965. The age of complex multicellular life on Earth is about 600 million years, or 10 to the 88. The age of anatomically modern humans is about 300,000 years, or 10 to the 55. The age of writing, of recorded human history, is about 5,000 years, or 10 to the 37. Your entire lifespan, if you are fortunate, is about 100 years, or 10 to the 2. These numbers on the logarithmic scale are clustered together. Human civilization, human history, human life, they all fall in the range from 10 to the 2 to 10 to the 5. The age of the Earth is 10 to the 965. The age of the universe is 10 to the 10 These feel far apart because we usually think of them linearly, but on the logarithmic scale, they are relatively close. Now consider the future, the end of the Stelliferous Era. The death of the last red dwarf is at 10 to the 14. That is a factor of 10 to the 4 away from the current age of the universe, 10,000 times further in the future than the current age of the universe from the Big Bang. And that is just the end of the Stelliferous Era, the beginning. The evaporation of the last stellar mass black holes is at 10 to the 77. The evaporation of the most massive supermassive black holes is at 10 to the 100. The timescales of proton decay are around 10 to the 40. The timescale for quantum tunneling of white dwarfs to iron is 10 to the 1500. These numbers are so far beyond the current age of the universe, so far beyond the entire Stelliferous Era, that they make the history of everything we have ever known, all of human civilization, all of complex life, all of the Earth, all of the Sun's lifetime, look like an infinitesimal point at the very beginning. And yet, from inside the Stelliferous Era, from the perspective of the burning stars and the living planets and the thinking minds, all of this is real. The Dark Era is as real as the Stelliferous Era. The evaporation of the last black hole is as real as the formation of the first star. The physics that predicts these outcomes is the same physics that describes the nuclear reactions in the sun's core and the chemical reactions in your cells. The universe does not care about our timescales. It operates on its own timescales, from the femtoseconds of particle physics to the incomprehensible eons of black hole evaporation. We are adapted to perceive timescales of seconds and years and decades. The universe operates on all timescales simultaneously, and the ones that matter to us are a tiny and unrepresentative slice. But here is what I want you to take from tonight's journey. The fact that the Stelliferous Era is brief on the cosmic timescale does not make it less real. The fact that the Dark Era is much longer does not make the Stelliferous Era less important. Importance and duration are not the same thing. The most important things are often the briefest. A spark lasts for a fraction of a second. A supernova peaks in days. A civilization lasts for thousands of years. All of these are brief on the cosmic scale. None of them is less real or less significant for being brief. The Stelliferous Era is brief on the cosmic scale. It is also the only era in which complexity, life, and mind are possible. The only era in which the universe can understand itself. The only era in which the questions we are asking tonight can be asked at all. That makes it, by any measure, the most important era of the universe's existence. The long dark eras before and after it are the context. The Stelliferous Era is the content, and we are in it, right now. In the middle of the universe's most productive, most complex, most remarkable period, the stars will go out, the black holes will evaporate, the universe will grow dark and cold and still. All of this will happen, the physics is clear. But right now, tonight, the fires are burning, the stars are shining, the galaxies are alive with light and motion and chemistry. And in one small corner of one ordinary galaxy, on one small planet orbiting one ordinary star, some minds are looking up and tracing the full arc of the universe's story, from the first moments after the Big Bang to the final evaporation of the last black hole, and finding themselves somehow in the brief, bright middle of it all. That is us. That is tonight. The universe made us curious enough to ask where it is going, and we found out. Sleep well. Good night. There is one more thing I want to say before we close tonight. It is about what it means to take seriously the full timescale of the universe's future, not just as an intellectual exercise, but as something that changes how you see things. Most of our thinking about time is anchored in human timescales. We think about our lives, about decades, about the span of civilization, occasionally about geological time or the age of the Earth. We rarely think about millions of years, let alone billions, let alone the trillion-year timescales of the Stelliferous Era's decline or the incomprehensible timescales of the black hole era. But the universe operates on all of these timescales. The red dwarf that will be the last star in the Milky Way is burning right now, at this moment, somewhere in the galaxy. It is unremarkable, dim and small, probably not visible to the naked eye. It will still be burning long after the sun has expanded into a red giant and consumed the inner solar system. It will still be burning long after every other sun-like star in the galaxy has died. It is, right now, one of the longest-lived objects in the universe, and it will become the longest-lived, persisting for trillions of years while everything brighter goes dark around it. And the supermassive black hole at the center of the Milky Way, Sagittarius A star, is right now, at this moment, accreting material and occasionally producing flares of radiation visible to radio telescopes. It has been there for billions of years and will be there for billions more. And eventually, long after the last star in the galaxy has gone dark, it will begin to evaporate through Hawking radiation, and after a period of time so vast it defies naming, it will emit its last burst of radiation and cease to exist. All of these things are real. They are happening on different timescales, but they are all part of the same physical story. The same laws of physics that govern the nuclear reactions in your body govern the Hawking evaporation of black holes on timescales 100 orders of magnitude longer. The same equations that describe the oscillations of a pendulum describe the orbital mechanics of merging galaxies on timescales of billions of years. Physics does not care about timescale. It operates on all timescales with equal validity. Understanding this, really internalizing it, is what it means to think like a physicist. To see the universe not as divided into the human scale and the cosmic scale, with different rules for each, but as a single physical system, governed by a single set of laws operating on all scales simultaneously. The nuclear reactions in the sun are the same quantum mechanical processes that will eventually cause proton decay in the far future, just at different temperatures and densities. The gravity that holds you to the Earth is the same gravity that will eventually cause the Milky Way and Andromeda to merge, and the same gravity that will eventually cause the most massive black holes to accrete their final particles before evaporating. It is all one story, one set of laws, one physical universe, operating on every timescale from the Planck time to the heat death, and we are part of it. We are not outside the universe, looking in. We are inside it, made of it, governed by it, embedded in its particular moment. The atoms in our bodies were forged in stars that lived and died before the sun was born. The carbon in our cells was synthesized in the core of a dying star and expelled in its final death throes. The iron in our blood was created in a supernova explosion. We are, in the most literal sense, the universe organized into a form that can contemplate its own past and future. Tonight we contemplated its future. We traced the path from here to the Stelliferous Era's end, through the Degenerate Era, through the Black Hole Era, to the Dark Era. We looked at the physics of each stage and found that the physics is clear and the timeline is vast. We found that the universe has a long, quiet future ahead of it, and that the brief burning present is the most remarkable thing that has ever happened or will ever happen within it. And now we stop, not because there is nothing more to say, but because the night is long and the stars are still shining, and sometimes it is enough to know where you are. You are in the Stelliferous Era. You are in the brief, burning, complex, remarkable middle of the universe's story. You are made of star stuff. You are powered by nuclear fire. You are watching the universe with curiosity and care, asking where it is going, understanding the answer, and finding yourself grateful to be here for it. That is enough. Sleep well. The universe will continue its slow journey from fire to darkness. The stars will keep burning for billions of years more. The dark era is coming, but it is far away. And right now, tonight, the fires are still burning. Good night.